All right, thank you, Dr. Arnold. Good morning, everyone. As Dr. Arnold mentioned, I'm Sumit Sharma. I work as irrigation water management extension specialist in the Panhandle of Oklahoma, um, and I worked on sampling probes and organic carbon sequestration measurements during my master's project when I was here at OSU doing my master's with Dr. Warren. So I'll be talking about sampling probes impact on bulk density and look into some methods of calculating organic carbon stocks in soil. So I'll just go over some basic which have been covered in earlier presentations. That organic carbon is useful. It's helps with soil structure, helps with microbial communities, nutrient cycling. It's a useful soil health indicator. And agriculture soils have long been recognized as potential source and sink of atmospheric carbon dioxide, and that depends upon anthropogenic activities, how we deal with it, whether it's going to act as a source or sink. So if we till the soil, it's going to act as source. If we do more conservation practices, it may sequester some carbon in its reserves. And that's why soil organic carbon has been considered for carbon credits. But there are some issues that how to estimate these carbon credits, because estimating soil organic carbon is challenging due to spatial and temporal variation. And it varies from one part of the field to the other, and it may vary between in a small area within the field itself. So the error in estimation is not only due to the variation in space or time, but it can also be due to the bias that is introduced while we collect samples from the field, and these biases can be in estimation of soil organic carbon concentration, or they can be in the measurement of bulk density. Now, these issues have been known for a long time, and people have been dealing with them since 70s. But most of the effort has been on the methods that the math that we use to calculate or estimate the soil organic carbon stocks in soil. And relatively limited attention has been given to the sampling equipment and their impact in our estimation. So in this presentation, I will be presenting some of our findings from the one project that we did about 9-10 years ago. So just to give a little brief account of how it is estimated. So the first and simple or relatively simple approach is that you go out in the field, you take a core, and then you segment it into whatever depth you want to, and you calculate its bulk density, and you analyze the soil organic carbon concentration in your segment. You multiply these two, and then you multiply it with an area conversion factor to find out the tons of carbon per unit area, whether it's acre or hectare. But the issue with that is that bulk density is dynamic in nature. So you have taken samples today, and 5 years later, you come back to take samples. You're taking samples on shrinking or swelling soil. So your bulk density may be different this time. Or some of your soil has eroded, or some more material has deposited on it. So your surface has moved. And if you're going to a fixed depth, that is, say, if you're going up to 30 centimeters, so your area or the volume that you're getting this time is different. In other sense, or the other way we can say it is that, say, you have accumulated organic matter in the topsoil. Now this has declined your bulk density. So your bulk density numbers has gone down, but concentration is up. So you probably won't see any change. So these are the issues that we run into when it comes with bulk density. But there's also that when we are taking some samples from the field, there could be compaction due to sampling probes, or sample may break, or could be contamination or human error. So these needs to be looked at when we are looking into the estimations for credits. The next method, so this method is called spatial coordinate approach. I will refer to it as fixed depth, or FD, from here on. And the next method to eliminate this issue with bulk density, so it's called cumulative mass coordinate approach. I call it fixed soil mass, or some people call it equivalent soil mass. I will refer to it as fixed mass from here on as FM. And this one, bulk density is replaced with mass of soil. So we do not measure soil organic carbon stock in, say, a 10 centimeter layer. We will measure it in soil mass of soil layer, and that mass is fixed. And now the issue with this was that how would you determine the mass of soil that you're going to use? For depth, you can say I can go to 10 centimeters, or I can go to 20 centimeters. But for mass, many scientists have proposed different things. That earlier they were proposing that, well, let's use genetic horizons and see how much soil mass is in there, and then that's how we will go for it. But determining a genetic horizon, it really depends upon a person to person. It's judgment while he's collecting sample, because it's sometimes the horizons are not abruptly demarcated. Sometimes it's a gradual change. So then there comes that, well, you can do different cores and use a minimum or maximum mass of soil that you are getting from these cores, and I will explain it in the next slide. So any extra, if you are doing minimum, any extra soil you can adjust with the adjacent layer, the layer below it, or if you are getting short on soil mass, you can take some soil from the lower layer. You adjust it, so you just fix the mass instead of fixing the depth. So how it works is that, so just imagine if I went into the field and I took a core with a sample, with the probe, and the next time I am going to the field, and for the first time I determined how much mass I've got, and I did from all these cores, and I decided I'm going to use the minimum mass in each layer. Next time I'm going there, and the soil is a little bit compacted, and I took the sample. So this time that, so if this was 10 centimeter layer, 1, 2, 3, so up to 30 centimeters. This time, if it is compacted, I can get the equivalent mass for the first layer in, say, 8 centimeter, because it's compacted. So I will use that mass, and any additional mass, I will adjust it or add it to the lower layer. And any extra mass from the second layer, I'm going to add it to the third layer, and whatever is left, we can discard. Now, if we do maximum mass, I will have to take some, if and there is no compaction, I may have to take some mass from lower layer and add it to the upper layer. And eventually at the end, at the last layer, if I run out of soil, then I may have to go back and take some longer course, and if I have not taken them in the first sampling. So that's how this thing works. And it was proposed in 2009, and all these equations over here just put my words into numbers. So now this I have said for in temporal terms. That is, I took this core the first time, and then I went to take the core the second time. But this can be applied if I'm comparing probes as well. So I took this sample with a certain probe, and then I took this sample with a different probe, And of all the scores I have taken, I selected, okay, I'm going to stick with the minimum mass, and I can adjust course, the soil mass from other cores based on this probe. So that's how we conducted our analysis for this research, but just wanted to go a little over this method. So we did this project in 2011. It was a pilot project for Oklahoma Carbon Program, where we tried to design a sampling protocol to measure carbon credits for this program. The idea was to raise carbon credits through soil organic carbon sequestration in the no-till system, and farmers were gonna get incentives for raising these credits. So we went out in the field and collected soil samples from 19 fields from Major, Caddo, Garfield. There was one more county that I forgot, from 4 counties in Oklahoma. We used 3 probes to collect samples. So the first one was push probe with a diameter of 2.26 centimeters, the cutting edge diameter. The other one was hydraulic probe, about 4 centimeter diameter. And the third one was slide hammer probe, about 4.8 or 5 centimeter diameter. We took samples from in each field from a 3-meter radius area, which was selected randomly. We took 5 samples per probe from push probe and slide hammer, and we took 10 samples with the hydraulic probe. But for analysis, we just used 5 samples from the hydraulic probe, the first 5 samples. So the samples were taken up to 30 centimeters. They were segmented at 0 to 10, 10 to 20, and 20 to 30 centimeter layers. We brought them back in the lab, measured moisture. We measured soil organic carbon concentration, like total carbon, nitrogen. Through dry combustion, we measured bulk density, and we measured carbonates, and which we subtracted from total carbon to come up with soil organic carbon concentration in each sample. Now, since we are comparing the methods, we are comparing the probes, we also wanted to see the sample size that we will need if we go back to measure the carbon stocks raised in those fields. And we wanted to see how many samples we will need to detect that change with a 90% confidence power. So we used a power analysis in SAS 9.4 to determine the sample size required for and why we needed to see this, because sampling takes money, it takes time. So it's you want to, if you're doing a protocol, you want to be efficient. And then so the OCC had estimates that the potential of carbon sequestration in this area of Oklahoma was about 0.27 ton per year. So we wanted to see that how many samples we will need if we want to detect a change of 1 ton with a 90% confidence. That means that if I go back and I take X number of samples, I'm 90% confident that I will detect this change. So I just used 1/4 ton per year just to keep things simple. Now, just looking at some of the results. So this is the bulk density for 0 to 10, 10 to 20, and 20 to 30 centimeters for 19 fields that we sampled. And we do see some significant differences, but when we look at them closely, we don't see much consistency. So bulk density does vary, and probe does have impact on its measurements, but determining whether one probe is dominating the other it was difficult to conclude. But we can say that the push probe, which is the smallest diameter, was dominating in the surface layer, and both the slide hammer and push probe were dominating in the lower layers. The one reason that this could be is because the push probe has smaller diameter, so it tends to exert more pressure as we shove it in the ground. And both slide hammer and push probe, when we were taking samples, the soil was usually dry, and sometimes we had to hammer them down, hammer them in the soil. So that may also have some impact that we cannot rule out. So this was the bulk density data, and we definitely see the sampling probes are going to impact our measurements, variable measurements that are gonna, and if there is this bias, probably we'll see in the carbon stock estimation. For soil organic soil organic carbon concentration, this is in percent. So there is some differences were observed between the probes, but they were very limited to about 4 fields in the 0 to 10, and about three fields in the second layer, and the differences tends to be more in more fields in the lowest layer. But this is in percent, and this difference is very, very small. So it's kind of inconsequential if you are multiplying it with, so for 100 kilograms, a difference of 0.05% is 0.5 kilogram. 100 kilogram soil, it's 0.5 kilogram of organic carbon. So moving on with this organic carbon concentration, when we calculated the estimates of soil organic carbon in the soil with the fixed depth method, where we use bulk density, and fixed mass method, there were 5 fields where we saw significant difference in carbon stocks among the probes. But if we replace the bulk density with soil mass, fixed soil mass in this method, that difference is reduced to 2 probes. And that is it's a combination of these 2 fields also have significantly different organic carbon. So it's difficult to tell, but yes, this fixed mass tends to reduce the variation, but it doesn't eliminate completely the difference between the probes. When we look at the variation among the probe, if how fixed depth or fixed mass, this should be FM, fared, overall fixed mass reduced the variation among the probes, but it was very slightly. It was only 2%. So what I can say from this thing, that for both methods, you can see significant differences between the probes, but the variation might be reduced in the fixed mass method, but with this data, it was very slight, only 2%. But and it's average, but it depends upon field to field. So some fields had very small, and some field had large reduction in the variation among the probes, and even in 3 fields, fixed mass had higher variation. So it's the method tends to work, but more investigation is required. For sample size, so power analysis uses the standard deviation and the mean difference you are investigating, or you are hoping to detect. So I did 1 ton accumulation for 4 years and plotted standard deviation of all fixed mass and fixed depth together. And this is sample size, this is standard deviation, and it ranged from 7 samples for a standard deviation of 0.29 to about 1,480 samples for a standard deviation of 6 in our first sampling. So So the uniformity of the field and this number of sample that we need is within that 3-meter radius circle to detect a change. Overall, if we compare the fixed mass and fixed depth, the for each probe the standard deviation was reduced, and this is average, and then the sample size also tends to decrease by 50 samples for fixed mass, but it's still quite a lot. And if and this is for the standard deviation for 0 to 30 soil organic carbon stock. This is not for one layer. And if somebody says that we have seen that most of the carbon accumulation is in the surface layer, and when we just look at that surface layer, the standard deviation is lower at 0 to 10 centimeter a layer, whether we do for the soil mass for this layer or whether we do it the fixed depth. And even if out of that 1 ton, half of it is accumulated in this layer, we will still need about 171 samples for fixed mass and 270 for fixed depth to detect this change. But if we increase the detection limit to 1 ton in the surface layer, then we will need only 45 samples in the 3-meter radius. So what does that mean is that if in soils where we have higher variation, we can wait a little bit longer to detect any change, so it will help in reducing the cost and time for sampling. So this is one of the challenges that we can look at when it comes to estimating the organic carbon stocks in field. There is still some work needs to be done. Some of it is done this decade, and I will try to share some discussion of what we did to do, which we could have done, and it could be useful for designing protocols. So one of the things that we did assume in this field, that I have talked about bulk density in this data, but what about organic carbon? The organic carbon, we assume that linear interpolation. What does that mean? That the organic carbon changes abruptly from one layer to the other. So that we used one concentration for the first layer, one concentration for second layer and third layer. So this recent work from Wendt et al. Shows that a linear interpolation, when you do linear interpolation, the estimation of cumulative organic carbon mass may be not maybe, but has a little bit more root mean square error. So you tend to have a little bit higher variation. And on but he proposed a cubic spline fit that he says that the organic carbon concentration tend to change more gradually. But this is applicable only for analysis where we are looking into multiple layers, not on if we are looking single layer. And the
Sumit, we lost your audio.
Okay, hear me now? Can you guys hear me?
Yes, sir.
All right, I'm sorry about that.
2-minute warning.
All right, sir. Yeah. So yeah, so that's one thing that we didn't look into this this data analysis that we did, but there are more things that we could do or somebody can consider when they are sampling. That is that removal of plant residue before sampling. be careful with that, because these things can make a difference. Measure the core length once you are out of, once you take the core, you have gone up to 30 centimeter and you take the core out, measure its length. If it's really 30 centimeter, if it is shortened, then it's compacted. Time of sampling. We took samples during the winter time because microbial activity is lowest at that time due to low temperatures. And then selection of fixed mass. You can do minimum or maximum. I would recommend minimum because it saves time, and you don't have. If you run out of sample, you can for minimum you probably won't run out of sample, but for maximum, if you run out of sample, you probably will have to go back, or you will have to take longer course. And management history has a role to play in this, in the performance or carbon stock estimation. Luckily, we did not have any rocks present in our soil, but those are things to be considered. And based on literature review, you cannot rule them out from your estimations, because they are part of your soil and that soil texture. So some soils, we saw some data earlier today. Some soils, like say coarse texture soil, have low potential of accumulation, so detection limits may be reduced or may wait longer to be reasonable with our sample size to detect considerable accumulation. So all these things need to be considered, and what we learned from this project. Now for the summary, this project showed us the sampling probes do impact the bulk density, which in turn is going to impact our soil organic carbon estimates. Small diameter probe tend to compact the soil, and then hammering the push probe or slide hammer may also have some impact. So we cannot rule out human error in there. Different probes used for sampling cores, they may give us different estimates. But fixed mass can reduce the estimate, but not enough to eliminate variation variation within the field, and to reduce, and it may not be enough to reduce the sample size required to detect any accumulation. So sample size in our case was large due to low accumulation rates in Oklahoma. So sampling intervals can be increased to accumulate large detectable differences to reduce sample size, but that will depend from field to field and its potential, how much it's going to accumulate per unit time. And with that, I'll just be open for questions. This is my information, and this project was funded by OCC, and we'll thank everybody who helped me with this project.